Okay, so hello students. So let us go to next topic. So we have uh, completed all about postulates, tools. Now it's time to apply all this thing, and let's see whatever we have done is have some worth or not. So obviously the postulates is the ultimate thing, and we have to apply it again and again on different type of system. So now we will just go for the application of that postulates and mainly on just a minute. Okay, so we are just going to apply all these postulates and onto different type of system. So first system is very primitive system, obviously free particle. So we will just try to see without any potential, if particle is free, how quantum mechanical thing can be analyzed. And most important thing is that when you are analyzing the quantum mechanical thing, we have to just try to compare it with a classical thing because we know the classical observation. So let's try to first do little bit of classical mechanics. So what will happen in a classical mechanics, and then we will just try to go for a quantum mechanical treatment of free particle. The free particle contribute a simple first Schrodinger wave equation of free particle, and then using the step potential to identify what is behavior of a particle when it is going to interact with step potential. So these two things we just want to talk. So obviously free particle means particle is moving with the constant momentum. So momentum px is constant. Momentum px is constant. So classically, what will be Hamiltonian? The Hamiltonian is all about px square upon 2m. And you know the equation of motion for the Hamiltonian. So you have del h upon del x, that will be equal to minus px dot, and that will be 0. So you can say px is some constant c. And next you can just find del h upon del px is equal to x dot, and this will be px upon m is equal to x dot, and this x dot is nothing but dx upon dt. So you can just find dx upon dt. I have calculated px as a c, so this will be c upon m, and now I can write x as c by m into t plus some constant alpha, and let's say this is alpha naught. So this is a particular trajectory you can find, and in this trajectory we can predict what will be value of position with the time. After time t, how is this going to change? This is position versus time. But now let's try to do this experiment again and again, because actually our purpose is to try to understand quantum mechanics. So what we are going to do, we are just doing this experiment again and again, and I am taking it very simple. At t is equal to 0, I just want to find what will be the position. So what will happen? Suppose first time I am going to do this experiment. What is the position? I can just easily put t is equal to 0. Position is alpha naught. Next time, again I am going to next experiment, and same system, same initial condition. What I am going to do? Again I am getting this is alpha naught. So if you are going to repeat it 100 times, every time you will get alpha naught at t is equal to 0. And if you want to find the average value of position, so what is average value of position? That is alpha naught plus alpha naught up to alpha naught, and you are talking 100 time, and that will be 100, that will be alpha naught. If I want to calculate that x square, if I want to calculate x square, then you can just calculate alpha naught square, alpha naught square. You will just go for alpha naught square by 100, and that is 100 into alpha naught square. This is all about x square. What will be value of delta x? The value of delta x is about x square minus x whole square, and that value, sorry, this is again alpha naught, sorry, this is alpha naught square, 100 time alpha naught square. What I will get, alpha naught square minus alpha naught square, that will be 0. Now, if I want to write a one particular probability distribution function for all the event at t is equal to 0, can you suggest any probability distribution whose expectation value is 0? Means what is meaning of that? Sorry, the error is 0. What is meaning of that? Meaning of that, there is deterministic. Value is deterministic, and there is not dispersion. So every data is at same point. Every data is at same point. So what you have, I can find a beautiful distribution, and that distribution can be something like this. And that distribution I can write with what? Dirac delta function. Isn't it? At some x is equal to alpha naught. Isn't it? And this value is alpha naught. So this is all getting the probability. And so what you will get? You will find the particle precisely at the value of alpha naught at any time at t is equal to 0. This is x, and this is probability density, rho x or fx you can write. So what you can find? You can find in a classical mechanics, hence the state of a system is deterministic. You can precisely say where is the particle. And I am 100% sure that at t is equal to 0, particle at particular alpha naught. Similarly, at next particular time, I can also predict. Next particular time, I am also predict the thing, and I am going to predict it with 100% assurity. And so in the classical mechanics, you can find this is well predictable. If you have any doubt, you can just ask me. Now, let's try to go for this. Let's try to understand this thing quantum mechanically. So quantum mechanically, what are the state of a system? Is the solution of, basically, we have to just see the time evolution. How with the time, the state is going to change. Then obviously we have to just solve what? Schrodinger wave equation. So let's try to, first time we are going to solve Schrodinger wave equation and for the free particle. And this is very simple because you have done your mathematical physics very nicely. So it will, I have to just explain my concept. Everything you have done earlier. So now we are just talking about the Hamiltonian operator. And this Hamiltonian operator is nothing but px square operator upon 2m. Because potential is 0. And what I have to do, I have to find h psi x is equal to e, or let's say this phi x, okay? E phi x. What is h? H is nothing, px square upon 2m phi x is equal to e phi x. What we are going to do, we will just write it in operator form. So this will be minus h cut square upon 2m, and you can write del square phi x upon del x square is equal to E phi x. Now this thing is minus h cut square upon 2m d square phi x upon dx square is equal to E phi x. So what will happen? You can just write this all thing as d square phi x upon dx square is equal to 2me upon h cut square phi x. So obviously this number this is minus sign, huh? So this will be minus. So you can write, because I can change del to d because only one variable is there. So there is not any mathematical mistake. So del square phi x or d square phi x plus 2me upon h cut square phi x is equal to 0. I can write this whole term d square phi x upon dx square plus k square phi x is equal to 0. So what are the solution? The solution is phi x is equal to e to the power ikx. Let's say some coefficient is there. And another solution, so I am taking it phi plus. Another solution is phi minus. So that will be a e to the power minus ikx. So these are the solution. And these are the eigenfunction actually. These are the eigenfunction. So what will be the eigenvalue? So eigenvalue will depend. So you can easily find the eigenvalue. So how you can get the eigenvalue? You can get the value of k square. So k square is equal to 2me upon h cut square. So I can get the value of E for given value of k. E is equal to h cut square k square upon 2m. And please, these eigenvalues are associated with both of function. So this is associated with h cut square k square upon 2m. So what is energy eigenvalue? H cut square k square by 2m. So obviously they are what? Degenerate eigenvalue. They are what? Degenerate eigenfunction, isn't it? Because this eigenfunction is also associated with this eigenvalue. This eigenfunction will also associated with this eigenvalue. What is physical meaning of that? What is physical meaning of that? Can anybody explain what is physical meaning of that? Why we have two eigenfunction with the same energy? Obviously, two direction of motion. Very nice answer. Means you have two momentum direction, isn't it? Either you will go for the positive momentum or you can go for the negative momentum, and both momentum can be incorporated, and both state will say about the two different momentum. How you can see? You can just measure the momentum eigenfunction. So if you are going to measure the momentum part, then how you can write it? So suppose I will measure px phi plus x. What is px? Px is minus I h cut del upon del x. And let's say this will be a, and you can tell it a plus and a minus, okay? Because due to some fact. So I can write a plus e to the power ikx. What you will get? You will just differentiate it. You will get ik. I minus 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 is plus sign. So you will get h cut k e to the power ikx. So what you have? This is, and this is a plus actually, a plus. So you can write px phi plus x is equal to h cut k phi plus x. So what is eigenvalue? H cut k. So for this particular function, the energy is associated h cut square k square by 2m. But what is momentum associated? The momentum associated is h cut k. Similarly, the momentum associated with this particular thing is also minus h cut k. So what we are representing? We are representing actually two different directions. The state will say about the two different directions. One is going into positive side and another is going into negative side. And the positive side will have momentum h cut k, and negative side have momentum minus h cut k. And if you have momentum h cut k and minus h cut k, you have same energy. Because what is energy? The energy is all about px square upon 2m. Either you will take plus h cut k or minus h cut k, you will get same thing, h cut square k square upon 2m. So these two have different momentum but same energy eigenvalue. So why for one dimensional free particle has basically doubly degenerate eigenvalue, or you have two eigenfunction corresponds to one eigenvalue. Up to this, if you are comfortable, then you can, if you have any doubt, you can just ask me. Okay, so let's go for actual thing. Let's go for actual thing. So I am just erasing this thing. Now look at, this is the so let's try to get it easily. So what you can say, so there is phi plus is all about, let's say, a plus e to the power I kx. Phi minus is a minus e to the power minus I kx. Madam, please mute kar lo. Okay. So phi plus and phi minus is there. So both have energy eigenvalue h cut square k square upon 2m. The momentum is h cut k and this momentum is minus h cut k. Okay, so we have just done it. This is the final information. Now let's try to make any state psi. Any state, not, I am not using the kit now because the kit is not relevant in free particle actually. Suppose I just want to make any state psi and I am making it very simple, deliberately. And let's say this is something e to the power I kx plus e to the power minus I kx. Let's say some a. I can take this a as any number. I can make a state because any superposition of a state is a state. This allows us to find the state. So, and that I can assume this is at t is equal to 0. So what will happen at t is equal to t? So at t is equal to t, you can just find psi x, and don't worry, a plus a minus will incorporate it into a. So I have taken this mathematical liberty that I can choose any coefficient. So don't worry about this. So this will be e to the power I kx and e to the power minus I et upon h cut according to postulate 5. And second function is also taking the same eigen value. So this is also e to the power minus I et upon h cut. Isn't it? So we are very fortunate. And what is value of E? The value of E is basically h cut square k square upon 2m. So I am just using E here. So what is psi x t? So this is a psi x t. Psi x t is something e to the power minus I et upon h cut. And this is something h square. I am not using again and again this thing. It will just make it clumsy. E to the power I kx plus e to the power minus I kx. So what I can do, I can write this function as cos function, and a is also there, isn't it? So can I write this function as cos function? Yes, we can write as a cos function. So what will be psi xt? So psi xt, I can write it as a some cos function. So let's say 2a e to the power minus I et upon h cut cos kx, isn't it? They are something cos kx. A 2 is here, so this will be cos kx. What will be psi star? Psi star is, let's say, 2a star e to the power minus I minus plus I t upon h cut, and this function is again remain cos kx. But I am interested to get the probability density. So what will be probability density? So mod psi square is all about psi star psi, so I can take it directly. So you can write 4 mod a square, and this will be cancel out each other thing. So this will be cos square kx. I can use this as a number, new number. 4 into a square is again some a, deliberately I am taking. So that will be, let's say, some c square cos square kx. So I can draw this probability density. I can draw right now. Are you comfortable up to this? And don't worry, this type of manipulation of calculation, this is very obvious in quantum mechanics. But main thing is all about this cos square. This number can be anything, depends on situation. So are you comfortable up to this?
Yes, sir.
Okay, okay. Because some people have difficulty to note down, so why I am taking time. Okay, so let's try to understand this thing. And please, this is very ideal situation. This is very ideal situation. So, but it's a very interesting thing. What will happen? I can plot this. And this is at some t is equal to t. And it is independent of time, so every time it will be remain same. What will be plot? Plot will be something like this, isn't it? Obviously, there is some problem, but let's talk actually mod psi square x. What is problem? I will tell you later. But right now, you have this kind of situation. How you can get this thing? How you can get this particular thing? Suppose I am talking about, suppose I confine my particle between this and this. Okay. I am just going to confine my particle because taking x minus infinity plus infinity is a very idealistic thing. So let's try to confine the particle between this and this. That such that I can make a wall on both sides, and I just want to confine a particle between this. And we will discuss it into particle in box also. But right now I am just going to confine the particle between, let's say, 0 to a kind of situation. Now what will happen? In the first measurement, maybe particle is here. Second measurement, maybe particle is here. Third measurement, maybe particle is here. Fourth measurement, maybe because there is probability to find the particle between 0 to 8 anywhere you can find. Isn't it? You can find there is some probability to find the particle anywhere between, in fact, from minus infinity to plus infinity, but deliberately I have confined particle between 0 to a. You can have probability to find the particle anywhere. At the same time, you have same time. What is meaning of same time? Means if you have 1,000 number of particle and you are just giving the initial condition same, what will happen to classical mechanics? The classical mechanics, every particle is at this point. So you have Dirac delta. Every particle is this point. Let's say this point is alpha naught. But in a quantum mechanics, You have same initial condition, same function. You are just sending the 100 particle or 1000 particle. What will happen? Some particle will be distributed here, some distributed here, some distributed, and more distributed here, more distributed, less distributed. Then we have something this kind of formulation. The distribution of a particle will something like this. Or you can say it another way. That another way you can say that how you can get this thing. So in first measurement, your particle is here. You will just note down. The second measurement, your particle is here. You can just note down. The third measurement particle is here. Sorry, on here. Again here. Again here. Again here. Again here. Then if you are taking the distribution, you will just get something like this. Just like this. What is this? How this can be happen? This is a wonderful explanation. So what you can say that in a classical mechanics, the state of a system is precisely deterministic. But in quantum mechanics, the state of a system is not deterministic. Rather, it is extended from minus infinity to plus infinity. And there is finite probability to find the particle between some x to x plus dx. You can find this area x to x plus dx, and this area will tell you all about the probability density. So this is the ultimate thing, that your state of a system, hence your state of a system is extended from minus infinity to plus infinity. Your probability density is also distributed from minus infinity to plus infinity. What is meaning of that? At same particular time, there is probability that particle can found at this point also, and it may be found at this point also. The thing is that the probability can be changed, but there is certain probability to find the particle at any point from minus infinity to plus infinity. This is the wonderful expression we can get from the entirely different thing from the classical mechanics. Obviously, the way to doing the classical mechanics, I have a little bit changed, and I have do this experiment again and again, such that I can just correlate this thing with quantum mechanics, because I have taken the quantum mechanics more weightage here. So I just try to do the classical mechanics in a quantum mechanics way. Then also what I can find the particle is actually precisely deterministic, but here the particle is not deterministic. There is probability distribution of a state, then distribution is again, there is probability distribution to find the particle between x to x plus dx. So this is all the story of free particle. But there is some problem. What is this problem? This is not normalized. This is not normalized. If you will do from minus infinity to plus infinity, it will not 1. So you cannot normalize. So if you cannot normalize, you cannot use as a kit operator. And this is very obvious, because it is very tough such that you can have particle from minus infinity to plus infinity in a practical sense. So you have to confine the particle in some limit. At the macroscopic level, obviously there is some limit. But theoretically, yes, there is particle from minus infinity to plus infinity. There is finite probability. Why there is finite probability? Because wave function is extended. The state is extended. So what we have learned? We have learned the state of a system is extended. The state of a system extended to minus infinity to extended between minus infinity to plus infinity. And you can say this is in a very important thing, that is extended wave function. So they are wave function. So what is solution of Schrodinger wave equation is identified as what? Wave function. They are named as wave function. And they are also known as energy eigenstate. Okay. So if you have any doubt, you can just ask me.
Sir, at time t What do we mean at time t? At that particular second, we are making
Yes,
time
yes,
be
yes,
like in
yes,
minutes.
yes, yes. At particular second. At particular second.
So on that particular second, we are making so many measurements.
Yes, you cannot say that your particle is only here. Very good. Yes.
Okay.
But here you can say, nahi?
Yes.
Exactly, exactly. Very, very nice question. Very nice question. Very good. Good, good, good way to approach the problem. Very good.
Thank you, sir.
Okay. So, are you getting it? So let's go for next thing that will be, we will just try to understand basically probability current density. Then we will go for step potential. Okay. Just a minute. Okay. So let's go for probability current density. So what is probability current density? Is let's say they are defined at Jx and for the one dimension, and this is given by h cut upon 2im psi star del psi upon del x minus psi del psi star upon del x. So this is your probability current density. Obviously, look at first analogy is very important in quantum mechanics because this is the most modern subject. So when it is modern subject, it is always take the analogy from different places. So analogy is all from continuity equation. So what is continuity equation? You can write del dot j plus del rho upon del t is equal to what? 0. I think you have heard this type of continuity equation. So there is not any continuity equation only in electrostat or electromagnetic theory or in statistical mechanics or in quantum mechanics. It's a very important thing. It will tell you something about the some quantity is going to preserve. Suppose in electrostat, we will just tell that total charge is going to preserve. Suppose in a basically stat mech, you can just tell if it is number density, rho is number density, then you can tell that total number of particle is going to conserve. So here in a quantum mechanics, we will just tell about the total probability of a system is going to conserve. And we have also seen that mod psi square will always same in even if time is going to change, mod psi square dx or that norms is going to same, something like this. But what we have this particular thing, j is equal to rho v. So what we have, this is current density. This current density is nothing but the charge density into velocity of a particle. This is all about current density is charge density into velocity of a particle. And please, charge density can be 0 even if there is rho density, but charge density can be 0 if velocity is 0. Means particle is static. So in an electrostat, what you can find? You can find if particle is static, then current density is 0. But if charge is moving or it is time varying, then there is current density. Now, let's try to get the some information from here. Let us go for just we have done one particular particle that is psi, and this psi is a e to the power I kx. Suppose I am taking this psi and just try to calculate what will be current density associated to this. And what will be mod psi square for this particle? Is mod psi square is mod a square. So this is your probability density, rho x. Let's try to calculate the jx. So when we are going to try to calculate the jx, this will be h cut upon 2im. This will be psi star is a star e to the power minus I kx. Del psi upon del x is all about, del psi upon del x is all about ik e to the power I kx, and you have a also. And next we are just going to write the psi. The psi is all about a e to the power I kx, and you will just differentiate to the psi star. Then this will be a star minus ik, and you have e to the power minus ikx. So what will happen? Ikx minus ikx will cancel to make it zero itself, and I and I is going to cancel out. The minus minus is plus. So I think you will get jx, and this will be mod a square h cut k upon m. So what is this particular thing? What is this particular thing? What is this value? This is nothing but the probability density. And what is h cut k? H cut k is nothing but the momentum by mass, that will be probability density into v. So exactly we have same type of situation, isn't it? So this is all about probability density into velocity, and velocity you can write px by m, and px is h cut k upon m. Similarly, for psi is equal to, let's say, a e to the power minus I kx, you can find jx as mod a square minus h cut k upon m. You can just calculate with yourself. But what I am going to do, I am just going to do the another example, and let's say the psi x is, let's say, a e to the power minus gamma x, something like this. And there is not ik part, e to the power ik part is there. So this is a complete real function. This is a real function. Now psi star will psi, so this will happen. Jx is equal to what? 0. Jx is going to 0. And you can have Jx is equal to 0, but you have mod psi square. And what is mod psi square? Mod a square e to the power minus 2 gamma x. And this is nothing but what? Probability density. This is nothing but, you can write this thing as probability density. And this is all about probability density. Now you can find there is probability density, but current can be 0. The probability current can be 0. Why probability current can be 0? If we can see with this analogy, then rho x is always there, 0. Sorry, rho is always there. Why it is 0? Because I can say there is px is equal to 0. And if you are going to apply px on this particular function, if you are going to apply px, then px is equal to minus I h cut del upon del x. If I am going to apply on this, minus I h cut del upon del x a e to the power minus gamma x. And what you will get? You will get I h cut gamma e to the power minus gamma x with a function. What you will get? You will get imaginary momentum with this function. So what is significant of imaginary momentum? What is significance of imaginary momentum? When you will get imaginary momentum? Classically, try to think classically. I am just asking to you. I need this answer.
Kinetic energy is negative.
Obviously, and in which region? In which region? Kinetic energy cannot be negative. Kinetic energy cannot be
Forbidden region.
exactly for the forbidden region. That's it. Means what we can expect there is particle in a classical forbidden region, even if its momentum is zero. Imaginary momentum means momentum is zero actually. Because Jx is zero, you can just calculate Jx is zero, imaginary momentum cannot exist. So I can say that Px is equal to zero with some logic. Means here you can just tell with the seeing Jx that even if Jx is zero, there is probability density. And Jx will be zero only in the region that will be classical forbidden region. So what you can find? You can find there may be existence of particle in a classical forbidden region. And classical forbidden region means classically the momentum is zero. This is nothing but the classical momentum. H cut k, sorry, the px will be all about, this px is all about classical momentum. So from the current density is zero, this doesn't mean that there is not any particle. Yes, there is particle. But the region is already classical forbidden region. And there is particle. Why we can say there is particle? Because probability density is not zero in that region. And this will works. You can see. We will see the tunneling and all about different stuff. And you can easily find this thing. Sometime in classical allowed region, there may be current density is zero because the particle, incoming particle have positive momentum, and after the reflection particle have negative momentum, then on an average momentum can be zero. So that is on an average zero. That is different issue. We will show you this thing in the particle in box when we are going to do. But when you are talking about any eigenstate, you will find there is the particle can be in the classical forbidden region. So let's try to understand each and everything in the respect of one particular system, that is step potential. So let's try to go for step potential. So this is all about step potential. So what is a step potential? So step potential is very interesting. This is zero. And let's say this is constant momentum, V naught. And you can throw the particle from left. So what will happen classically? So first case we are taking E is greater than V naught. So I am sending the particle at this energy level. So what will happen classically? If I will throw 100 particle, so for first particle, suppose I am taking the marble, what will happen? It will just cross it. Again, the same marble I am again sending it, it will cross it. If I am doing this experiment 100 times, it is going to cross it in another side. So it will just going to, it is impossible that particle can reflect back. It is impossible that particle is going to reflect back. But what will happen when we are doing this experiment with electrons? Then what will happen? We have seen that sometime particle can cross this barrier and sometime it can come back. how this event can be justified? Sometime it can just cross this barrier and sometime it can just come back. This is a very extraordinary situation. How we can explain it? And please, in a quantum mechanics or in any physics, first you will observe this thing and then try to apply the theory to justify this observation. It is not that due to your mathematics this observation is going to happen. You are just observing something and then you can justify the thing. This is very important. So let's try to get justification how this particular electron can be come back. And it is also seen if I will increase the energy higher and higher, then chance of electron to reflect back is less. But if I am taking it lower and lower, then there is chance of electron. So then there is higher chance of electron that will reflect back, even if energy is greater than V naught. So let's try to go for this. So obviously we have to just solve the Schrodinger wave equation into region 1 and region 2. So region 1 is a free particle, isn't it? So I can write minus h cut square 2m day square psi 1 del square del x square plus potential is 0 is equal to, let's say, E psi 1. And you can just find this. I have just solved it right now. So this psi 1 is equal to A e to the power I k1 x plus B e to the power minus I k1 x. What is value of k1? The value of k1 is all about root under 2me upon h cut square. Just I have done this problem just as a free particle. Now let's try to go for region 2. So what you can solve? You can just write minus h cut square upon 2m del square psi 2 upon del x square plus v naught psi 2 is equal to E psi 2. So what you can do? You can just write something like del को d लिख सकते हैं, d square psi dx square plus 2m. This will be E minus v naught upon, I am taking this side and I am doing it in this side. So minus minus plus, isn't it? So this thing will be again minus. So this will be psi 2 is equal to 0. E is greater than V naught. So there is not any problem. I can write this thing as del square psi 2. H cut square. Okay, okay. Del square psi 2 del x square. This is all about k2 square psi 2 is equal to 0. So what is k2? So you can find the k2 is all about, and you can just find the solution. The mathematical solution is psi 2. Let's say this is c e to the power I k2x plus d e to the power minus I k2x. And what will be k2? The k2 is all about root under 2m e minus v naught upon h cut square. Okay, so these two are right now. Just copy it, then we will go for next level. Okay, so now what is going to happen? So obviously I can assume the particle is coming from minus infinity. So what I can say, this is my incident wave. Sorry, this is my incident wave. This is my psi incident. Okay, because I assume this is incident, then what will be this wave? Reflected. Because you have logic. Look at the logic. Don't worry. This logic is from light. Suppose it has refractive index mu1, it has refractive index mu2. If some light is coming here, it is just go into another side and it will go back. Another side light will only go back if you have different region here, isn't it? So now here is only two region, region 1 and region 2. So this is region 1 and this is region 2. What is meaning of refractive index is different? Meaning that the speed of light is different into two region. And yes, speed of light is different into two region. Here it has different momentum, and here it is different momentum because the k value is going to change, isn't it? So speed of light is different. Sorry, speed of particle is different here and different here. So I can analogically tell it. So if this is the incident wave, so incident wave have which type of momentum? H cut k1. Then what will be reflected wave? Reflected wave have same magnitude but opposite direction. So what will be momentum associated to this? Minus h cut k1. Minus sign will tell you that opposite direction. So obviously this is in the region 1. So I can say this is the reflected particle. This is the reflected particle. And now, what about transmitted particle? The transmitted particle have different speed or different momentum, but same direction of the incident. These two have same direction. So I can identify this thing as transmitted particle, transmitted wave. This thing as transmitted wave. Now, what is physical significance of this one?
Reflection.
Reflection in the second region. But reflection can be happen if I will have different speed of the particle in this region. It is not going to possible. So this is not physically accepted. So this is not physically accepted. What we can put? We can put D is equal to 0. Are you getting this thing? Because logic must be always there. Or we are not doing mathematics. We are doing the physics. So from here, what we can say, we can make a conclusion that D is equal to 0. And suppose particle is coming from this direction, then which quantity is going to 0?
C.
C is not 0. Then obviously the particle is coming here, the incident wave, this is incident, this is reflected, then this is transmitted, then A can be 0. Even if particle will come into this region, there is also reflection and transmission kind of thing with the analogy. So just think it carefully, and I will start from this point in the next class. Okay. So if you have a sorry, why D is equal to 0?
Sir?
Sorry, आवाज नहीं आ रही आपकी.
Can you explain that once again? Why D is equals to 0?
Just take the analogy. This is the incident wave and this is the reflected wave in a light, in optics. So incident wave and reflected wave will remain in same region, but both have opposite velocity or opposite momentum. So look at here. Incident wave, reflected wave have same region and both have opposite momentum. Now once wave is transmitted, it will be again reflected when there is change in velocity or there is change in medium. Suppose here is mu3, then you have this particular thing. But here you have only two medium. So there is not anything which is going to reflect back. So if this is transmitted, then this cannot be reflected into second region. Isn't it?
Yes, sir. Okay, sir.
Okay. So why we have deliberately taken D is equal to 0. So I will just going to finish it tomorrow, and tomorrow we will just finish it, and we will also start particle in box. So everything is free particle. Okay.
Thank you, sir.
Thank you. Thank you.